All right. So I think we have done. You have the sheet? Yeah. See, the trouble is I use this sheet for the other section as well, and I sometimes lose track of which one I did in here versus which one I did over there, you know? I don't think I've done. Have I done like exercise 13 here yet? 13 is the square root of 144 over y squared. Oh, you're fine. Is this one familiar? Okay. So to do this one, we go, okay, so that's the square root of 144 divided by the square root of y squared. And what is the square root of 144? 12. And what's the square root of y squared? So like, right, so like generally it would be the absolute value of y, but we're given that y is greater than 0. So it's just y, because the absolute value of y is just equal to y. So in other words, the square root of y squared is just equal to y, provided that y is positive or 0. But like more generally, you have to have absolute value there. But all of these exercises, like it's given that the variables are positive, so when we take the square root of something squared, we just get the thing again. Exercise 14. We've got 60 root 50 plus 7 times the square root of 32. And we're supposed to simplify this thing. So let's see, that's like 6 times the square root of, 10? 5 times 10, so 5 times 10. Oh, 5 times 2 times 5, right? Or 25 times. Oh, look at that. I should rewrite this. I should think of this as 2 times 25, shouldn't I? That would be smarter. Plus 7 square root of, what is that, 4 times 8? Or 4 times 2 times, oh, good grief. Oh, how about 16 times 2? That'd be smarter, wouldn't it? If I think of it that way, because then we just got, like 6 times the square root of 25 times the square root of 2 plus 7 times the square root of 16 times the square root of 2. Square root of 25 is 5. So like 6 times 5 is 30 root 2. And the square root of 16 is 4. 4 times 7 is 28, so we got plus 28 root 2. And so, 28. So what happens? We get 58 times the square root of 2. So, of course, if you have a calculator, right, you can double check this pretty easily, especially if you've got one that does the exact arithmetic or, let's see here. Exercise 15. We've got the square root of 10a plus 8 times the square root of 90a cubed. That was exercise 15. I'll write exercise 16 down here while I'm at it, which is root 12 plus 5 root 6 times root 12 minus 5 root 6. So what can we do to the one up above there? No idea? I think we can get a square root of 10 out of both of those, right? You already got it. spoiling me. That's good. All right, so let's see here. So the first one, I can write square root of 10, square root of a, right? This one, I can plus 8, square root of 9, square root of 10, right? The square root of a cubed. And now I could write that a squared times a, right? So I could write it like that if I wanted, you know? And so we've got a common square root of 10 I can factor out. And I got square root of a plus, this is 3, right? So 8 times 3 is 24. And then that's a. And that's square root of a. So I guess I could write that as, you know, square root of 10 times 1 plus 24a times square root of a. I mean, there's various. I personally like that answer, but honestly, like there's a lot of different ways you could write the answer here and simplify. It's not at all clear to me what the right answer should necessarily be here. I think it's open to debate. There's a possible answer. How about this next one? This one's easier, right? We just do what? We just multiply, right? So square root of 12 squared minus 5 root 12 root 6 plus 5 root 6 root 12 minus 25 root 6 squared. So what happens here? I mean, if you look at the pattern, it's not surprising, right? This is like a plus b times a minus b, right? So what happens is you just get, you know, a squared minus b squared is how that simplifies, right? So like the plus ba and the minus ab cancel out here. And we're just left with what? Right, what is the square root of 12 squared? That's 12, right? And what's that? 25 times what? What is square root of 6 squared? What is this? That's going to be 6, right? So it's 25 times 6, which is, 150. I think we get minus 138. And there you go. Exercise 17 is kind of similar to this one. Let's do that one. Now, past exercise 17, there's a new concept that we have to cover. But fortunately, everyone's here, so it's good, right? Let's see here. Exercise 17. 8 minus the square root of 3 times 7 plus the square root of 3. So we multiply, right? And so I get 8 times 7, which is 56, plus 8 root 3, minus 7 root 3, minus the square root of 3 squared. So what's that? 56. 8 minus 7 is 1, right? So just plus root 3. And what's the square root of 3 squared? 3, right? So we just have minus 3 there, right? So answer 53 plus the square root of 3. So these aren't bad, right? Yeah, we should be able to get these. Shouldn't be a big deal. Now, so the next topic is rationalizing denominators. So the way I see it, there's a few common patterns, right? So the one is you've got like stuff over like the square root of 3, right? And so what you do is you just do whatever that stuff is, and you do like square root of 3 over square root of 3. So all of these tricks, they're all going to be like multiplying by the number 1. So that's like the common pattern here. So I'm just multiplying by 1, but I chose my number 1 in such a way that it's going to remove the radical. So another way to say this is removing radical from denominator. So downstairs we have root 3 times root 3, which is what? Yeah. Square root of 3 times square root of 3, what is that? I mean, it's the same as the square root of 3 squared, right? Yeah, it's just 3. So see what happened? We had a radical in the denominator to start with, and then after multiplying by the number 1, the radical's gone. There's a similar thing that you can do if you've got like, you know, square root of a minus the square root of b even. It'll still work for this. If you do blah, whatever that is, times the square root of a plus the square root of b, so multiply by, instead of minus plus, then upstairs you'll get blah times whatever, you know. But downstairs you get square root of a times square root of a, which is a. And then you get, well, so I'll write it out, square root of a squared plus the square root of a square root of b minus the square root of b square root of a minus the square root of b squared. And so what we have here is blah, whatever that was, times the square root of a plus the square root of b divided by, well, these terms cancel, and we're just left with a squared minus b squared. And if instead you had like yada over, you know, 3 plus, I'll go back to numbers, 3 plus root 2, if you take this and you multiply by 3 minus root 2 over 3 minus root 2, this trick will work to remove the radical, because that gives me 9. I get minus root 3 root 2, I get plus 3 root 2, so those cancel. And then I have minus the square root of 2 squared, which is just 2. So as you can see, like if we multiply fractions by the right kind of number 1, we can remove the radical from downstairs. We can also do this for complex numbers. Like if I have 3 over 4 plus 2i, right? I can multiply that. By the way, I mean, this is another notation for that would be 3 over 4 plus 2 times the square root of minus 1, right? So this is also, there's a radical here. We just use the I notation to kind of hide it, you know? But so by the same trick, we multiply by 4 minus 2i over 4 minus 2i. So just switch the one with the radical to minus. And when we multiply that through, we get 3 times 4 minus 2i over 16, you know, minus 8i plus 8i minus 4i squared. Notice that I squared is minus 1. So that's actually, these guys cancel. 16 minus a minus 4 gives me 20. So I get 12 upstairs minus 6i divided by 20. And one more step, that's 12 over 20 minus 6 over 20 I. This is the so-called Cartesian form of the complex number. So if we have a complex number and we write it in the form a plus ib, it's said to be in the Cartesian form. Like this to start with is not in Cartesian form. So if we use this rationalizing the denominator idea, we can take a complex number which is not in Cartesian form and convert it to Cartesian form. And I mean, that's interesting for a lot of reasons. But one of the reasons is if you wanted to plot complex numbers, we can plot complex numbers in what's called the complex plane. So like the complex plane has an imaginary axis, so-called imaginary axis, so-called real axis. And just to give you a few, like if I want to plot the number 1 plus I, it's here. Z is 1 plus I. See, I go 1 unit in the reals and I go 1 unit in the imaginaries, 1 plus I. If I wanted to plot W equals to minus 2 plus I, it would be the same I level, but it would be 2 left real. So it's like here. This is where W is. If I asked you to plot, 3 over 4 plus 2i in the complex plane, they'd be like, I don't know what to do. But if I asked you to plot this in the complex plane, it's easy. You just look for the one that's got like 12/20ths, which is what, 6/10. So this is like 0.6. What's that? That's minus 0.3. So I go over 0.6 and I go down 3. So it's like right here, That's where 1 over 4 plus 2i is in the complex plane. So the basic correspondence is just this. A plus ib corresponds to the ordered pair a comma b. That's how we plot complex numbers in the complex plane. There's a lot more to say about that, but that's just all I wanted to say for now. I'm just trying to explain to you, that's a reason we'd want to find the Cartesian form of a complex number. A lot of times we just say do it, and we don't ever explain why we were interested in it, I don't really have a good reason for why we're doing these ones. It's just a rite of passage, There are things that people called number theorists do with these kind of equations to reveal sort of hidden truths about prime factorizations of numbers, but we're not going to do that in this course. All right. So now that I've shared with you the basic strategies, let's try to work the problem. Exercise 18. Here we've got the square root of 17 over 3, which I'll start us out. That's the square root of 17 divided by the square root of 3. So what should we do? Multiply by what? Mm-hmm. Yeah, multiply this by what? To get rid of that 3 in the denominator. And remember, the name of the game is we can't change the value. We have to multiply by the number 1. We just have to multiply by the number 1 in such a way that we don't alter the value. So this is like pattern 1, stuff over root 3, right? So we should multiply by the square root of 3 over the square root of 3 in this one. So we've got, what's the square root of 3 times 17? What's 17 times 3? 51, right? So there you go. We move the radical upstairs. I mean, you could also write that as the square root of 3 times the square root of 17. That would also be fine. The point is we got the root 3 out of the denominator and re-expressed the number in a way which we don't have a radical in the denominator. So how can we rationalize this one? What should I put there? Mm-hmm. So square root of 2 plus, well, almost square root of 2 minus minus the square root of 5. Right, that should work for us. Let's work it out. So good, the radicals downstairs canceled out, right? And left us with a 2. And over here is a 5, right? So actually 2 minus 5 was minus 3. So like minus 1 over 3 times whatever is in the numerator, which is what? 8 root 2 minus 8 root 5 plus the square root of 10. And then minus 5. There you go. See, this one doesn't, simplify down like the other ones. Because you've got a square root of 2 and a square root of 5 floating around, It complicates the story a little bit. Which one should we do next? $20? Yeah, that makes sense. Let's see here. That does make sense, but I'm going to skip ahead to exercise 29 because this one's kind of like the same flavor as what we're doing right now. So this one's 2 minus 4i over 8i. So my suggestion is that we take this, I'll write it again for clarity here. Multiply by 1. What one should we multiply, though? Remember, I squared is minus 1, right? Well, negative 1 won't fix the, if I put minus 1 here, I mean, you could do that. That's allowed, but it doesn't help us because like minus 1 times 8i is still minus 8i. Instead of put I? Yeah. So let's try like minus I over minus I. I mean, you could do that. We could try that. Let's see if that works. So 2 times minus I, right, plus, plus 4i squared, right? And down here I've got minus 8i squared, which is, so that's minus 4 minus 2i divided by, what's that? Right, yeah, negative 8 times minus 1, right? Which is just 8 again, right? So this is really minus 4 over 8 minus 2 over 8 times I, which of course we could simplify further. That's minus 1/2 minus 1/4 I. There, I've written my answer again in the Cartesian form, you know? Let me make up one more of these. It's not on the sheet, you know? Let's do another one. What if we had like, let's see here, 2 plus I divided by, let's say, 3 minus 4i. All right, we want to write that in Cartesian form. What should we do? Yeah, we want to fix this, right? We want to get I out of the denominator, so we should do what? We should multiply by not 3 minus 4i, but we should multiply by what's called the complex conjugate of the denominator. So the complex conjugate of 3 minus 4i is denoted like this, like 3 minus 4i complex conjugate is the notation that people use for changing the term with I to like from minus to plus or from plus to minus. So you've seen this before? Yeah, maybe not, but it's okay. So 3 plus 4i. 3 plus 4i is going to work for us. I'll tell you more about the complex conjugate here in just a second, but we'll finish this example first. So 2 times 3 is 6. 2 times 4 is 8. So 8i plus 3i plus 4i squared. Downstairs, I get 9 plus 12i minus 12i minus 16i squared. So what's the denominator simplify to? It actually simplifies to 9 plus 16, right? Which is 25. And upstairs, this is minus 1, so 6 minus 4 is 2. And then plus 11i. So answer 2 over 25 plus 11 over 25 times I. So there's a pattern we should keep seeing with the complex numbers. It's even simpler. Like the ones that have square root of a real number, where we're rationalizing, it's kind of ugly. There's a pattern you could find there, but the pattern's even easier in the complex case. So like here's some notation. If z is a complex number and it's x plus iy, then the definition of complex conjugate, z bar, is x minus iy. So this is the so-called complex conjugate. And the neat theorem that we can always notice is that z bar, which is x plus iy, times x minus iy, how does that work out? So these guys cancel, right? And this gives us I minus I squared, which is minus a minus 1. So we just get x squared plus y squared. So geometrically, this is actually the distance from origin to x comma y squared. Because if you graph it, Pythagorean theorem. But the formula for getting that is just z bar. But the larger point here is that z bar is real. And so what that means is if we have something like w over z, and we want to make, and these are both complex numbers, if we look at that as w z bar over z bar, then we've just rationalized the denominator because this is x squared plus y squared. So we're just dividing by a real number. We actually saw that in the previous example over here. Notice that x squared plus y squared here is 9 plus 16, which is 25. Because 3 plus 3 minus 4i is actually distance 5 from the origin. Anyway, so just... And then the other section asked me, is that on the test? Do you have that in the homework? I'm like, no, not exactly, and no, but for your information, so you have a little bit more understanding about what complex numbers are and what this rationalizing trick has to do with distance. The problem that's actually on the test or the quiz is going to be more like the homework problems, which are just basically, hey, here's a complex number, put it in Cartesian form, or rewrite the complex number using the notation I is like another problem. Let me put those up here. Then we'll get back to exercise 21. Let me try to wrap up the complex part. So like the other so like exercise 26, it's almost stupid. Square root of minus 100, you're supposed to express with I. So the way I look at this is that that's the square root of minus 1 times 100. So I can look at that as the square root of minus 1 times the square root of 100. But that's I, by definition. And this is, well, that's 10. So actually this one is just 10I, you know? All there is to it. Exercise 27. Here you've got 3 minus the square root of minus 12. So there's a more general pattern to notice here. If a is a real number, then the square root of minus a is equal to I times the square root of a. So minus is, in some sense, a minus in a square root pulls out to be an I. We can think about it operationally like that. So I've got this minus. I can pull it out to get an I. That's all there is to it. Now, of course, the square root of 12 we could simplify, you know. It's what? That's 4 times 3. So square root of 4 times the square root of 3, which is 2 root 3. So this can be further reduced to 3 minus 2I square root of 3. I mean, that's just stylistically how I would write it. You know, you could put the 2 after the root 3. You could put the I. Like, the order of those factors is kind of immaterial. Just as a matter of style, I put it that way. It just looks right to me that way. Man, exercise 28 is the last one that I have, complex, here. And this one's, I mean, just, I really should have done this one first, you know? This one's easiest. I think this one's easiest because there's actually something, it seems like there's more to do. In some sense, exercise 26 is not easy because it's kind of like you look at it and you go, I don't even know what am I supposed to do, you know? 28 is easier in the sense that you know what you're supposed to do. You're supposed to multiply, you know? So you multiply, what do you got? 8 times 4, 32. 8 times 1 is 1, plus 8i. 9 times 4 is 36, so plus 36i. And then 9i times I is 9i squared. So plus 9i squared, which is actually minus 9, right? Because I squared is minus 1. So we've got 32 minus 9, which is 23. 8 plus 36, 44. So there you go. 23 plus 44i. That's out. All right, now let us circle back and deal with the algebra problems in this exercise set, right? So really the homework for chapters 5 and 6, which is what next quiz and test are based on, they really fall into sort of 3 categories, I would say. The first category is like simplify a rational expression. You know, we're like supposed to cancel factors and group like terms, stuff like that. And then, in some sense, rationalizing denominators kind of goes with that, right? But to start with, there was no radicals. Like chapter 5 is just rational expressions. There's no square roots. There's no cube roots. There's really not many cube roots in what we're doing at the moment either. Then we moved over to solving, solving equations, solving rational expressions. So that's one other class of problems, like solve rational expression equal to another rational expression, something like that. We had some problems like that. We almost solved almost all of them by cross multiplying, right? If you think back. And then the third topic, I would say, so maybe there's 4 topics actually. The one topic is simplifying rational expressions. The other topic is simplifying expressions involving radicals, right? And then there's solving equations involving rational expressions, and then there's solving equations involving radical expressions, right? Those are sort of the 4 food groups sorts here. And so let us turn now our attention to solving equations with radicals. So I might have done this one already, but I'll do it again. Exercise 20. Square root of 4x minus 17 equals to 1 is exercise 20. All right. So how are we going to solve that? What do you think we should do? What's that? I'll get us started. So what we do here is we just square the equation, like square both sides. That will get rid of the radical, right? Because if we take the square root of 4x minus 17 and I square it, I get 1 squared, right? But 1 squared is 1. What's the square root of 4x minus 17 squared? Well, that's just 4x minus 17. So that gives me 4x equals to 18. And then divide by 4, we get x equal to 18 over 4, right? Or you could simplify if you like, 9/2, right? So with these problems, anytime we make a step of squaring the equation, we should always really double check our answer. So let's check. 4 times 18 over 4 minus 17. I'm taking the square root of all that. What do I got? Square root of, 4's cancel, right? 8. So that's the square root of 1, right? Which is 1. So we're good, right? Let's look at exercise 21 then. So all of these problems, it's going to be the same story over and over again. Basically, the strategy is isolate the radical and then square it. All right? It's like pretty much always that. And sometimes the radical's already isolated. Like problem 20, the radical's already isolated, you know? This one, they've got a pesky minus 5 on the left-hand side. So before we can square it, we need to do something, which is to add 5, add 5 to the equation. So we get square root of y plus 1 equal to 6. Now we can square that, right? And that gives us y plus 1 equal to 36. So apparently y is equal to 35. Now we got to check our answer, right? Square root of 35 plus 1 minus 5 equals to the square root of 36 minus 5 equals to 6 minus 5 equals to 1. So this whole checking the answer thing is rather non-eventful at the moment, isn't it? All right, so exercise 22. So square root of x plus 7 equals to minus 2. Well, good. The radical's already isolated, right? That's good. So let's square it. See what happens, right? So we get x plus 7. And what's minus 2 squared? No? The negative goes away, right? So we just got 4 there. Just 4, yeah. So apparently x is equal to 4 minus 7, also known as minus 3, right? But let's check. So the square root of minus 3 plus 7 is the square root of 4. What's the square root of 4 equal to? 2. Yeah, 2. Is 2 equal to minus 2? It is not, right? So what's going on here? How is it that we got an answer, but the answer is not an answer? How'd that happen? Because you see what this tells me. At this point, I have lost the right to box that in. I got to say, nope, 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 nope. Mm-mm. How'd that happen? So the sneaky thing is that when we square the equation, we've actually adjoined a solution that was not there. Like when you square an equation, you can end up adding solutions in that were not there before. Think about it a different way. If instead we had this equation, square root of x plus 7 equals to 2, right? And you square that, you get to this equation just the same, right? But then that equation actually does have x equal minus 3 as a solution. So after we square the equation, we can't tell the difference between whether or not we started with this nonsense equation, which has no solution, or we started with this equation, which does have a solution. So that's the thing we have to be careful. When we square the equation, we can accidentally adjoin solutions which aren't really solutions. They're called extraneous solutions. An extraneous solution is a solution that your solution method produces, but in the end analysis, you have to throw it out. Kind of like the candidates in an election that didn't make it to the final round. Like in the previous election, like Ted Cruz was an extraneous candidate, for example. Like at the moment, this is a good question. Like, is Kamala Harris an extraneous candidate? Because we threw her out earlier, but then she come back again. So I don't know. Like I don't know what to say about that. I haven't thought about this much. Yeah. Now I like to think, because this is a little bit unsettling what just happened. I like to take a second and look at it graphically. So if we look at the graph y equals the square root of x plus 7, what is that? This is the y equals square root of x graph shifted what? Left. 7, right? So it's actually like this guy. For what it's worth, the range is 0 to infinity for this function, for this graph. Now, what does the graph y equals minus 2 look like? It's a horizontal line, right? Y equals minus 2 is like this. So when we think about this equation up here, to have a solution to that equation corresponds to the graph y equals square root of x plus 7 and the graph y equals minus 2 having an intersection point. But they don't. In contrast, if we put y equals to 2, it's a whole different story, right? Like y equals 2 would have a point of intersection, wouldn't it? And like I could plot that. Y equals 2 would be this, right? And the point of intersection is what we found, minus 3. My graph isn't quite right, obviously, because this is minus 7, but, So, I mean, there is a way of understanding when the solution doesn't work. You can dig into it and come to a deeper understanding. But we don't have to come to that deeper understanding for every problem. We square the equation, and we go back and we check. And if it doesn't work, then we're like, yeah, extraneous, ignore it. All right, let's see here. Exercise 23, we have x minus 8 equals the square root of x minus 6. This one's a little different, right? This one's a little bit different because now we've got a variable outside the radical. So what happens when you have a variable outside the radical is after you square it, you end up getting like a quadratic equation. Okay, so square it. Oh, the one of those had a 6. Yeah, that one. This one was 6. All right. So square both sides of the equation. And so we get x squared minus 16x plus 64 from foiling out this x minus 8 squared. And what's the square root of x minus 6 squared? Well, that's just x minus 6 again. Right? Okay, so I don't know how to solve that. But if I move all my x's to one side, then I got a quadratic equation, which I can either use quadratic formula, or I can try to factor if it's nice, or if that doesn't work, I can complete the square. So this gives me what? X squared minus 17x plus 70. Ooh, I think we can factor this one. Yeah? I think so. See if you can try. Like 70 is what? It's 7 times 10, right? Or it's minus 7 times minus 10. Because 17, well, minus 17 here, so we should try like minus 7 and minus 10. Because then we multiply this times that, we get 70. We get minus 7, we get minus 10, so minus 17. All right, so what are the solutions then? X equals to 7 and x equals to 10 are what I would call potential solutions. I say potential because it may or may not be the case that one or both of these is extraneous. How do we figure out which one? How do we figure out if they actually are a solution or not? Well, we got to go back and we got to plug it into the original problem before we squared it, right? So we look at x equal to 7. We get 7 minus 8 is equal to minus 1. And at that point, we can know that that's not going to be equal to the square root of 7 minus 6, which is equal to 1. And so there's something I should emphasize to you. Actually, just a general principle. In exercise 22, we didn't need to do everything that we did, actually. See, in exercise 22, we could have stopped at the very beginning. As soon as we got to this, we could have looked at this and said, hogwash. That's nonsense. Like, you can't have that, right? Like, you can't have, more generally, So like exercise 22 was square root of x plus 7 equal to minus 2, you know? And if you just look at that, we've got the square root of stuff is less than 0. But this is impossible. And so it doesn't matter what the stuff is. If you try to solve square root equal to negative, game over. We didn't need to square the equation. I did because I wanted to talk to you about the extraneous idea. But I knew there wouldn't be a solution before we squared it. So like once I get -1 here, I'm like, uh-oh, that's not going to work. I got -1 equal to a root. That's not going to work. Hopefully 10 works. Let's find out. So we've got 10 minus 8, which is 2. And does that equal the square root of 10 minus 6? Well, that's the square root of 4, which is equal to 2. Hooray. Yeah. So our solution is x equal to 10. Exercise 24 then. Here we have the square root of 2x plus 7 minus 2 equal to x. So what do I got to do here before I need to isolate the radical, right? So square. Well, we can't square yet because that. Right, so move the 2 to the other side, and so doing make it positive. All right, so x plus 2, great. Now we square both sides, right? And what happens? We get 2x plus 7 over here. We get x squared plus 4x plus 4 over there, right? Because when you multiply that out, that's what happens, right? If in doubt, write it out. And, okay, so x squared plus 2x minus 3, apparently, right? Now, that's a quadratic, and because I copied this from your homework, I believe this is going to factor nicely. If I had just made it up off the top of my head, there's no telling what would have happened to us. I want to say that that's x. I mean, get minus 3. You could use like 1 and minus 3 or minus 3 and 1. I said the same thing twice in a different order. That was stupid. We got a plus 2 here, so that means I want the plus 3 and the minus 1. But of course, when we unmultiply, we have to multiply to check, right? So plus 3x minus x gives me 2x. I get a minus 3. It's okay, it's good. So my potential solutions x equal to 1 and minus 3, these are potential solutions, right? And okay, great. Then now we try them out. So let's check.